Sure. Hi, everyone. I'm Gayathri Gururajan, and I'll be presenting my recent work on observation of neutral carbon in a sample of 29 high redshift dusty lens star-forming galaxies and the comparison of different mass traces. Oops. Okay. So to begin with, basically, in this work, we target a population of massive dusty star-forming galaxies with intense star formation rate greater than 500 solar masses a year. So if we see the plot on the right, it basically shows the star formation rate density as a function of molecular gas density. The black line here shows that galaxies can have an increase in star formation rate by having a larger molecular gas density or a larger gas reservoir. But there's also another population of galaxies here, shown in the black dotted line, where for the same amount of gas, you have a boost in star formation efficiency. Generally, it is suspected that for such intensely star-forming galaxies, there could be a combination of both a large gas reservoir as well as an increase in star formation efficiency. And in this work, what we try to understand is what drives the star formation in such intensely star-forming galaxies. And one way of doing so is by characterizing the gas reservoir, as it can give us some clues about the nature of these galaxies. So since we can't directly observe the molecular hydrogen content for these galaxies, we rely on gas tracers such as CO, neutral carbon line, dust, and C+. So CO is one of the most commonly and traditionally used tracer of molecular gas content of a galaxy. And in order to estimate the molecular gas mass of a galaxy from CO1 to 0, we'll need to assume a CO to H2 conversion factor. Now, the limitations of this is that the alpha CO does vary strongly with metallicity and density and can also be affected by physical processes like merger. Additionally, in most of these high Z dusty star-forming galaxies, the 1 to 0 transition is not really accessible, and thus we rely on higher J transitions. And in order to estimate the 1 to 0 luminosity from them, we'll need to assume an excitation fraction. Oh, sorry. The other method of doing this could be using the neutral carbon lines. Now, this has two transitions, and both of them are known to trace extended gas and remain excited over a large range of temperatures and densities. So if we see the formulation on the left, we'll need two factors. One is the C1 excitation factor, shown as the Q10 here. But this can be constrained if we can observe both the C1 transitions. And the second factor will be the C1 abundance, which will still need to be assumed, and it also varies with metallicity. The third way of estimating the molecular gas mass of a galaxy is through its dust mass. So when we estimate the dust mass from our SED modeling, by assuming a gas to dust ratio, we can estimate the molecular gas mass. But this gas to dust ratio, as shown in the plot on the right, also varies strongly with metallicity. The other way of doing this is by using the C+ line. Now, the C+ line is also known to trace molecular gas content, amongst other things. And by assuming a C+ to H2 conversion factor, we can estimate the C+ based molecular gas mass. And this factor, alpha C2, does not vary strongly with metallicity, and the C+ line is quite bright for these high Z DSFGs. So the main focus of this work is to understand the physical properties of the gas reservoirs of intensely star-forming galaxies, and is also to understand how efficient C1 line is as a tracer of molecular gas content, and whether these four tracers we use agree with each other or not, and is there a way we can cross-calibrate them. So to begin with, we use a sample of SPT SMGs, especially for which both the C1 line transitions are in the observable windows of ALMA. On the right, I show the C1 1 to 0 and C1 2 to 1 line profiles of one such galaxy. And for this sample, we also have a lot of ancillary data in terms of low J and mid J CO lines. We have the dust masses estimated, and we have some galaxies for which the C+ line is observed. Along with our ALMA ACA data, which mainly targets the C1 lines, the CO7 to 6 and CO4 to 3, we also have 9 apex observations of C+. So in the final sample, we have 29 SPT SMGs in the redshift range of 1.8 to 4.7, with both the C1 lines targeted, and 11 of them also have additional, 17 of them also have additional C+ data. So firstly, we try to understand the IR luminosity as a function of the C1 lines. So C1 being an extended gas tracer and IR being a tracer of star formation rate, this plot could basically show us a proxy to the integrated Kenniger-Schmidt relation. Now in the plot on the left, what we see is the C1 IR luminosity against the C1 1 to 0. And what we do basically is to constrain the slopes of just the SPT SMGs and including the SMG sample, the local and the main sequence galaxies, and also for a combined sample. What we see is that when we consider these samples individually, all of them have a more or less linear relation in terms of the IR and C1. But for a combined sample, which includes the SMGs and the local galaxies, the slope is more superlinear. This was suspected in a lot of studies in literature, and they proposed that this could be due to the difference in trends between the main sequence and the starbursts. But this effect is less pronounced in the case of C1 2 to 1 line, but this could be compensated by the higher excitation factor of C1 2 to 1 in starbursts. With line ratios, we can also constrain the properties of the ISM of these galaxies. For instance, more extended gas tracers such as C1, when compared to a higher JCO, which is more likely to trace the density, we can get a proxy to the density of the ISM of these galaxies. And by constraining the C1 to IR, which could be like the total gas versus the star formation, we can get an idea of the radiation field intensity of these galaxies. So basically in these two plots, what I show is the ancillary data for which consisting of SMGs, main sequence, and local galaxies. And the gray dot dashed and dashed lines here basically show the densities and radiation field from the PDR modeling. When we compare our galaxies to this sample, what we see is mostly the SPT SMGs have very similar radiation field intensity and densities as the other SMGs, but they're slightly higher than the local galaxies in spite there being an overlap. What we can also do from our data is to analyze the excitation temperature of these galaxies. Since we have both the C1 lines targeted, we can estimate the C1 excitation temperature. And in the plot on the right, we basically compare the C1 excitation temperature to the dust temperature of our sample with all the ancillary data that's available. And we see mostly that for most of our sources, there's a higher dust temperature than the C1 temperature, which could be possible if the dusty cores are more present in the center and are warmed by intense star formation, whereas C1 being more extended is present in less dense regions. We also don't see strong candidates that have a much higher excitation temperature than the dust temperature, thereby not favoring towards optically thick dust scenarios. So now we have 4 tracers, and all 4 of them have unknown factors in terms of the C1 abundance, the alpha CO gas to dust ratio, and the alpha C2. What we can do is to cross-calibrate these tracers in terms of all the other quantifiable or known quantities, and therefore get a relation between these tracers and see whether they're consistent or not. So basically what I mean by this is, if you look at the equation on the bottom left, we can get a function for the C1 abundance as a product of alpha CO in terms of the C1 and CO luminosities and the C1 excitation factor, which is shown in the plot right above it. And we see we compare it with the IR luminosity for our sample, as well as all the other data that's available for similar galaxies in literature. So in these plots, what we can see is that there's not a strong trend with the IR luminosity, and we don't see a strong scatter either. So basically with the 4 tracers, we can make 6 such cross-calibration relations. And these tracers do agree reasonably well with each other. And the amount of scatter that we see in these plots can be reproduced significantly by measurement uncertainties, and we don't see a strong trend with IR luminosity. So if we consider two different alpha CO regimes, one more Milky Way-like and one more Euler-like, we can get different values of these tracers. So a higher alpha CO gives you a low carbon abundance, a high GDR, and a high alpha C2. And a low alpha CO gives you very low GDR values, higher carbon abundance, and a low alpha C2. And both these values fall in the range of various factors constrained in similar studies in the literature. So basically, if we compare the depletion time scales estimated by both these alpha COs in the plot here against the redshift, what we can see is using a higher alpha CO indicates that our population is more likely to be in the main sequence dominated, and a lower alpha CO gives us much shorter depletion time scales, which is more suggestive of a starburst-like population. But with what we have right now, we can't really disentangle between these two populations. So to conclude, from the physical properties of these intensely star-forming DSFGs, we can see that the C1-IR relation is nearly linear for SMGs for both the C1 transitions, and the difference in the slope is less pronounced for C1221. The densities and radiation field intensities of these SPT SMGs are much similar to those of the SMGs in literature, but are higher than the main sequence and local galaxies. We find a median excitation temperature of 34.5 Kelvin, which is higher than some studies in the literature and comparable to others. And we find that the C1 excitation is always lower than the dust temperature for our sample. So the main uncertainty when it comes to the C1-based gas mass estimation still remains to be the carbon abundance. And by observing the two C1 transitions, we can constrain the Q1 to 0, which significantly reduces our uncertainties. And the C1-IR relation is much comparable with the CO-IR relation as well. And by what we can understand with these four tracers is that they do agree with each other quite well. And whatever scatter we see in their relation can be mainly reproduced by measurement uncertainties. And we don't see a strong trend in the IR luminosity. Thank you.
Thank you very much for this very nice talk. So are there any questions for our speaker?
Actually, I have, and apologize because it's not my field, so maybe they are very simple, obvious questions. So starting from your conclusions, the second point, yeah, no, the second, okay. Number 2, okay, the last point. So the slope are compatible, and so what this means physically? What this is saying, this?
So I think what I understand from this, I may be not completely correct, is that C1 and CO sort of trace similar regions and have similar properties maybe, and they seem to have a very similar relation with the IR. So maybe they're, so there was always this question of which gas tracer is present in which, is dominated by what sort of emission, and maybe this could mean that, but it could be, yeah.
Okay, thank you. And okay,
sure.
Sebastian, go ahead, and after, if there is time, I will ask again.
Sure.
Something else. Thank you very much.
So very interesting talk, Gayathri. Thank you very much. I have a question. Which scatter has the least, which tracer has the least scatter? And which one you think is the best then?
So basically, I think here we have the, so which tracer is the best? I would never be able to answer this question.
I know it's a provocative question. But okay.
Yeah, no, but we would need something extra. Like, for instance, if we can compare all these with dynamical masses, or if we have metallicity estimates, maybe we'll get an idea of what suits these sort of galaxies better. But I feel that from our results, it's mainly the the C1CO seems to have a tight relation. And the C1 GDR does have a scatter, but the most scatter is in terms of alpha C2. Whenever we compare any of these traces with alpha C2, it seems to have a stronger scatter than the others. But again, this scatter is not really like too significant because we don't have any p-values less than 0.05. So we can't really conclude that there's a strong, most of them, it could be intrinsic, but with our data, we can't really, disentangle what is intrinsic and what's measurement driven. But
somehow it's the good news. They're as good as each other. Okay.
That they agree with each other, it's already like really good to know.
Okay, thanks.
Thank you.
So Piyush, please, you can unmute yourself and ask your question.
Thank you. Hi, Gayathri, really nice talk. So I had a question on the C+. Is it a better tracer of the star formation rate or the molecular gas mass? Where do we stand on that as of now?
I'm really, really not an expert on this at all. So it's I think from 2019 more strongly that they're starting to advocate that C+ could be a more likely molecular gas tracer as well as the star formation. And I think there are I think there's one paper by David Wisgen where he did like this sort of analysis on mock data of many simulated galaxies with C+, and he found that it seems to be a better molecular gas tracer, but I still do have my doubts. So we really need to understand what dominates the C+ in the ISM of the galaxy. So I don't think I know the answer to this question.
No worries. Thank you.
Thank you.
I don't know if there is some more time for other questions.
Yeah, I think we have still a couple of more minutes. So if you have any
Okay,
questions.
so I have a question. I heard at some point that you said some sources in your sample for 29 sources, correct? You talked about mergers. You mean galaxy mergers?
Yeah, but I don't think we have an idea of how many of these galaxies are merging.
Okay, because my question was, I expect that when there is a merger, there is a Barsistan formation or a quenching or something. So my question was, did you see something strange with respect to the other, let's say, normal sources or not?
So I think with this sample, we didn't really, so it's quite shallow, the data. It's more, so we can't really get hints of it. But we did go on another study with three galaxies, very similar to this. And out of the three, one was most likely a merger candidate. So there could be a fraction of them being dominated by more merger-like. But to quantify this, it might be difficult. And plus, these galaxies are lens. So we would really need to work on our lens modeling in order to do that. But when we went high res, we did find out of three, there was already one. So maybe if we can do something similar with this larger sample, I would be able to understand that.
Perfect.